Hey y'all, this is the first example in chapter 16.1. We have a wheel, which soon this thing will have some mass to it, and we're going to see how torques affect that. But right now we're just looking at the relationships of position, angular velocity, and angular acceleration. So we have a wheel with a known radius 0.2 meters. The motion is going to go in this direction because we're going to apply a force right here. They give us that force as 4t. It's a function of time, and if you think about the acceleration right here at any point p, so at this instant it's going to have a tangential component, but it's also going to have some radial component. To figure out the rotational motion in this problem, for this one we're only going to need to look at the tangential component. Okay, so initially at rest, and that's when theta is equal to 0 along this line right here. Force is applied to the cord, we know the force, and that's going to cause an acceleration. Start noting that that's the tangential component though. What they want to find is the angular velocity of the wheel, omega, and the angular position of the line, OP. That's this thing right here. What is the angle it's going to sweep through in radians? And they don't give us time, so we're going to get our answers as functions of time. Okay, so we don't need the normal or radial component to our acceleration for this problem. We just need the tangential component, so just don't need. Let's start out with the relationship that the tangential component is equal to alpha r. We're just looking at perpendicular components, so we don't have to do a cross product. This is given to us as a function of t, and we know the radius as 0.2. So we have alpha as a function of t now. And was that 20t? That would be radians per second squared. Alright, well, what we can do with that is go to a definition that alpha is the derivative of the angular velocity. So the angular acceleration is the time derivative of the angular velocity. If we rearrange that, I can say d omega is equal to alpha dt. We now have alpha as a function of time. Put it right there. So d omega is equal to 20t dt. And let's go ahead and integrate that. We wanted to know the angular position of OP in radians, and we're rotating, so let's go 0 to omega and 0 to t because it started from rest. Alright, integrating that will give you an omega equals to 10t squared, and the units for omega would be radians per second. Alright, so this is kind of a 3-in-1 problem. We can use one more definition and say d theta is equal to dt. That time derivative of theta, or the angular position, is equal to omega. We have omega now, so we can rearrange and say d theta is equal to omega dt. D theta is equal to, let's plug in 10t squared. And don't forget the dt, and let's integrate this. they asked for the angular position in radians. We would be normally given the time, but we can just integrate this from 0 to t for now, and 0 to theta, and that's going to give us 3.33, or 10 thirds t to the third, and then we're just down to radians at that point. So we started with alpha, or we got alpha, we got to omega, and then we got to theta. So if we knew how long the wheel rotated for, we could figure out what its alpha is at that moment. We could figure out what its angular velocity is and where its position is about that wheel.